My name is Xiaolong He, and I'm going to present deep autoencoders for nonlinear physics-constrained data-driven computational framework with an application to biological tissue modeling. And this work is in collaboration with Kai-Chi He from Pacific Northwest National Laboratory. This is the outline of my presentation. And I will first talk about the motivation of this work and then give you a brief overview of the physics-constrained data-driven computing. And then I will introduce the proposed auto-embedding data-driven computational framework for nonlinear materials modeling, where autoencoders are introduced to address some issues related to high dimensionality of the data and also the generalization ability of data-driven computing. And then I will also discuss some results of data-driven modeling of biological tissues with experimental data. So first, we all know classical computational mechanics is based on two very different types of equation. The first one is the well-accepted physical laws. For example, in computational solid mechanics, we have equilibrium and compatibility equations where we have unknown displacement and stress. And let me define the notation here. The F here is the deformation gradient, S is the second Piola-Kirchhoff stress, and E is the Green-Lagrangian strain, U is the displacement, and N is the normal to the boundary of the domain. And T is the traction on the traction boundary, and G is the prescribed displacement. And B here is the body force of the domain. And so here, in order to solve this boundary value problem, and traditionally, we will need material models that relate stress and strain. And traditionally, we use the phenomenological constitutive modeling based on physical intuition and mathematical assumptions to obtain these material models. And experimental data of the material samples is used to identify the material parameters in the material models. However, this phenomenological constitutive modeling step introduces errors and makes the material models lack generality for complex materials. For example, for here for the skeletal muscles, we have multiple highly nonlinear and anisotropic components. And it will be difficult for phenomenological modeling method to construct material models for this kind of biological materials. And in the past few years, physics-constrained data-driven computational framework have been developed. And the objective is to directly integrate material data into simulations. And by formulating the boundary value problems into an optimization problem under the physical constraints, and this enforces the physical constraint strongly. And here, let me define some notation before I move on. And we define a state as a strain and stress pair, and a hat is used to denote the parameters of materials, and capital E is a material database that contain material data points from experiment, and epsilon is a material admissible set of the materials. And E here is a subset of the material database is a subset of the material admissible set, epsilon. And correspondingly, the C here is a physical admissible set that contains all physical states that satisfy the physical constraints or physical equations here. So we also define a distance functional to measure the distance between the material state and the physical state as shown here. And the figure on at the bottom here shows a schematic of the physics-constrained data-driven computing. And every material point in the system have two states. One is the material state, and the other one is the physical state. And so the data-driven framework is solved to minimize the distance between these two states of every material point in the system through a fixed point global local iterations. And finally, the data-driven solution will be a state that satisfies the physical constraints and also closest to the material database of the materials considered. So the physical constraints are imposed in the global step minimization, and the local step is to search for the optimal material response that is closest to the physical state from the global step. I will talk about more details in here. In the global step, we are given the material state of the material point or integration point. If finds a physical state from the physical or the admissible set to minimize the distance functional between these two states. And this is a minimization problem subject to physical constraint, including the equilibrium and traction boundary conditions. And it can be solved by using the Lagrange multiplier and a nonlinear solver, such as finite element and mesh method. And in the local step, the distance minimization data-driven framework finds the material state from the original material database that is closest to the physical state from the global step. And alpha here denote the index of integration point. And here the direct searching of the optimal material data from the material database can result in undesirable solutions, especially when the material database contains noise and outliers. And so in this data-driven framework, the global and local step iterations are performed at all integration points until convergence. And the local step data search of the data-driven computational framework developed so far operate in the original space of the material data point. And this can be high dimensional, for example, in three-dimensional analysis. The feature dimension can be 12, for example, including 6 independent strain component and 6 independent stress component. And this high feature dimension could result in requirement of a large amount of data in order to achieve desirable convergence performance for the data-driven computing. So to address the high dimensionality issues and also enhance the generalization ability of data-driven computing, we introduced the autoencoders for material manifold learning. And the autoencoder contains an encoder and a decoder. An encoder is trained to compress high dimensional input data, extract a meaningful underlying data structure, and store it in the low dimensional embedding layer. And a decoder is trained to reconstruct from the embedding to a high dimensional data that is closest to the input data. And this low dimensional embedding layer enables noise filtering and dimensionality reduction to extract the underlying data structures of the material data. And the deep network architectures also enables autoencoders to learn complex nonlinear manifolds with exponentially less data than the non-parametric methods based on nearest neighbor graph. And this train, one of the very good benefit of using autoencoders for data for manifold learning, and that is beneficial to data-driven computing, is that the trained autoencoders define explicit mappings between the high-dimensional space and the low-dimensional embedding space, and this enables efficient data projection between these two spaces, and this is particularly attractive for data-driven computing. Here is a schematic comparison between the proposed auto-embedding data-driven approach and a local convexity data-driven approach proposed by Kaiji He and J.S. Chen. And let me first introduce the local convexity data-driven. And here I want to make a comparison of this proposed framework and the existing framework. In the local convexity data-driven approach, given the physical state from the global step, it first searches for several nearest neighbors from the material database, and then construct a local convex manifold denoted by the black dashed line here. And the optimal material state is reconstructed within this local convex manifold. And this local convex reconstruction expands the feasible solution space for the robust data-driven iterations against noise and outliers. and it improves the robustness of data-driven computing. However, all the local data searching and reconstruction operations of this local complexity data-driven framework operates in the high-dimensional data space of the material data. And doing online computation with a non-negative least square solver. And this can be computationally expensive, especially when we are dealing with high-dimensional when we're dealing with a large data set and a large scale system. So in the proposed auto-embedding data-driven framework here, an autoencoder is first trained offline to learn a low-dimensional global manifold of the material data, denoted by the orange dashed line here. And then once it is trained, the trained autoencoder is used in the auto-embedding data-driven solver to project the material data point and the physical state from the high-dimensional data space to the embedding space. And then the reconstruction and local data reconstruction are all performed in the embedding space through an efficient convex reconstruction, which enhances computational efficiency and the generalization ability. I will talk more details about the procedures of this framework in the second. So we refer the data space of the material data as a high-dimensional space, while the embedding space as a low-dimensional space. And the trained encoder projects the data from the high-dimensional data space to the low-dimensional embedding space, while the decoder does the opposite. And previously, we have defined here D and Z hat as the physical state and material state in the high-dimensional data space, respectively. And now we add a prime to these parameters to denote the corresponding physical state and material state in the embedding space. In this proposed auto-embedding data-driven computation framework, the global step remains unchanged, the same as the one introduced before, while the local step here, it is divided into 3 sub-steps. And I will introduce in the next slide in more details here. So in this auto-embedding data-driven solver, the offline trained autoencoder is first used to project the original high-dimensional material data point from the high-dimensional data space to the embedding space. And then in the local step, the physical state from the global step are first projected by the encoder to the data space, denoted by this white triangle. And then in the embedding projected to the embedding space. And then several neighbors closest to the projected physical state in the embedding space are sought, and then they form a local convex manifold. And we use a efficient convex reconstruction to find the optimal material state in the embedding space that is closest to the projected physical state, denoted by the square here. And then in the last step, this optimal material state in the embedding space is projected back to the data space by the trained decoder. And this complete one local step. And then the global local iteration continues until the convergence. And this is the local step of the auto-embedding data-driven local solver. And here in the embedding space, we have a local convex reconstruction. And this reconstruction is based on a Sherpa interpolation scheme that uses reproducing kernel shape function. And we introduce a 0-order basis in the basis vector in the reproducing kernel shape function so that we get a 0-order reproducing kernel shape function. And we define the kernel function as an inverse distance function so that the reproducing kernel shape function satisfy partition unity and positivity. And they can be used for efficient convex reconstruction. And the example on the right here shows that we have 3 example data points denoted by the stars in different colors. And the blue circles are the nearest or closest material data point to the given data point. So the squares here are the reconstructed data points using the Shepard interpolation scheme. You can see that all the reconstructed points are located within this local convex space formed by the nearest neighbors. And this shows the convexity of this interpolation scheme. And this interpolation function, interpolance, zero order reproducing kernel function is very efficient, can be efficiently constructed. And that enhances the online computational efficiency. And also it expands the feasible solution space for robust data-driven iterations. It's the first example of the data-driven modeling of hyperelastic beam under large deflection with 4 synthetic noisy material datasets generated by using the Sanguine and Kirchhoff material models. The figures below here are the 4 noisy synthetic datasets. The top row is the 3-dimensional strain dataset, and the bottom row is the 3-dimensional stress dataset. We investigated 5 different initialization for the autoencoder training and 3 different architectures. And because of the symmetry of the autoencoder, we used the encoder architecture to denote the autoencoder architecture. For example, for an encoder with an architecture of 643, it means that the encoder has 6 units in the input layer, 4 units in the hidden layer, and 3 units in the embedding layer. And the autoencoders are first trained using these synthetic strain and stress data, and then applied in the online data-driven computing. The solutions here shows this is the deformed configuration of our data-driven predictions, and also denoted by the red dot. The blue circles are the solution using the constitutive model-based solutions, and we can see that our data-driven solution agree well with the constitutive model-based solutions. And then the figure at the bottom left here shows the normalized tip deflection of our data-driven solutions with using the noisy material data set, and also the reference solution is in the black line. It shows that our proposed approach produces very robust predictions compared with the local convexity data-driven. When the material data set contains some noise, it starts to get some deviation in the prediction. And also the result in our proposed approach also takes less number of iterations. And
sorry for interruption. Yeah, we have only 1 minute left. So.
Okay, sure, thanks. Yeah, it shows that our proposed approach can also achieve a high computational efficiency. I think I will jump over this. And the proposed approach is further evaluated using by modeling the biological tissue with experimental data, and including 9 biaxial stretching protocols and 2 pure shear protocols. And here for the biaxial stretching protocol, C is the circumferential direction, R stands for the radial direction. We have various loading ratio in these 2 directions. And because of the symmetry of the model, we use a quarter model in our data-driven simulations. This is the strain and stress data of all the protocols, Green Lagrangian strain and second Piola-Kirchhoff stress. And this strain and stress data I used to train the autoencoder. And then the trained autoencoder is then applied in the data-driven simulations under the deformation of a certain protocol that is not used in training. And for example, here we have 2 cases. In the first case, we have data from the protocols 1, 3, 4, 7, and 8 used for training autoencoders. And then after training, the trained autoencoder is applied in data-driven prediction of protocol of the responses of biological tissue subjected to the deformation of protocol 5. And these data-driven prediction are compared with the experimental stress data of the protocol 5. And here, the figure shows that the result shows that our proposed approach can predict pretty well regarding the stress response of the biological tissue compared with the local convexity data-driven approach. And in the second case, it also yields a better generalization performance and higher accuracy. And this is because the proposed approach, the data search of the proposed approach is based on the low-dimensional embedding space sought by the autoencoder, and this enhances the accuracy and generalization ability. So in summary, we introduce deep autoencoders and the efficient convexity reconstruction to enhance the generalization ability, computation efficiency, and robustness against noise of the data-driven computing. And thank you.